All right, so let me welcome Mike Strickland back for the second installment of his seminars here at UCP. I don't think I have to do a long introduction because everybody in the audience actually has heard last week's introduction. Let me just emphasize that this one piece of work that I remember most that he did was a torturous, humongous hard thermal loop calculation to get complicated QCD corrections under control. So Mike is somebody who clearly likes to attack hard problems. So with further ado, let's have him tell us more about this hard problem that he's attacking right now, and give us a bit of an idea of how the landscape around this is looking. All right.
Okay.
Get it going.
For the kind introduction. I will note in this connection, however, that hard problem, which we worked for 15 years to solve in the end, I never received a dime of funding from anyone because nobody was interested. They wanted phenomenology. So I had to learn at the same time how to solve hard problems and how to do phenomenology. So that's why we're here today and talking about bottomonium suppression, because you also have to be able to address what's seen experimentally. All right, so picking up from where we left off last time, we were talking about bottomonium suppression, and I had sort of introduced you to bottomonium. Bottomonium is a bound state of a bottom quark and an anti-bottom quark. The mass of this bottom quark is on the order of 5 GeV, and the mass of the bound states, as you can see here, on the order of 10 GeV as a result. As a result of this very large mass, I'll discuss this in more detail as we go, you can treat this system non-relativistically to first approximation and get a good description of the spectrum for all the states. In some sense, you can think of it as a tiny little height, kind of like muonium, but with very, very heavy muons, right? All right, so another bit of lingo that I have to introduce for students who may not be aware, normally these observed states are color singlets, right? So the upsilon-1s has a color and anti-color quark stuck together so that it's a colorless hadron. That means it can be observed physically. But for some short amount of times, you can also form unbound pairs of quarks and anti-quarks. For example, a red and an anti-blue, which would give you a color octet state. And in fact, in high energy production, you typically produce the octet states first through the decay of a gluon, which is in the octet. And then that octet state of a QQ-bar pair, then one of the quarks will radiate off another gluon, and then it will become a singlet at a later time. Now, in the context of the quark-gluon plasmas, we're going to see you have to take into account the existence of both of these states, because as let's say we start with a singlet state flying through the quark-gluon plasma, it might encounter a gluon. It's going to get kicked into an octet state. At a later time, it might radiate off that gluon, and then it'll go back to the singlet. So you can't just have a description that's solely in terms of the bound states. You also have to have a description that can also describe these unbound states. Now, because of their large binding energy, as I said last time, these heavy quark bound states become special in the sense that, if I just cross above the phase transition temperature, I might melt all the light hadronic states, but some of these guys will survive, and I can use the survival probability to tell me something about the quark-gluon plasma. We saw this slide last time, but I just wanted to remind you. So there are two effects, and I'll go through detailed slides to try to explain this more. Going back into the 80s, the idea was that, well, if I have a plasma around, I'm going to have Debye screening. I'll explain what that is, at least pictorially and with some simple equations in a couple of slides. Essentially what it means is that the long range part of the interaction is screened out, and states that are bound can then become unbound. This is mathematically an effect that occurs in the real part of the potential between a heavy quark and a heavy anti-quark. What was discovered roughly 16 years ago by Mikolainen and company in Bielefeld was that, well, if you sit down and you just seriously take the hard thermal loop propagator and try to compute the potential between two heavy quarks, you get this screening effect, but something else came along for the ride. And namely is that you got an imaginary part of the potential. And this imaginary part of the potential maps to larger spectral widths. If in traditional nuclear physics, you can think of this as the kind of optical theorem that you have some imaginary sort of scattering potential, and that would lead to widths which correspond to decays of the state, right? So how we observe these 1s, 2s, and 3s states is by looking primarily in the dimuon channel at high energies. You can also look in the dielectron channel, but there it's harder experimentally because the electrons are more affected by the magnets in the experiment. It's harder to reconstruct, but you can do it. And as we said last time, we have some background, and then we find three states sitting on top of them that you can clearly identify, which and by reading off the center of this peak, you can actually just read off the mass of these three states. And then if you could sit in the middle of the quark-gluon plasma and repeat this experiment, what you would find is that at finite temperature, you would still have three peaks, but they would be much broader than those three peaks. And if I kept increasing the temperature, they just get broader and broader and broader until they're basically gone. Now, of course, you don't want to sit inside of a quark-gluon plasma for too long because it's 10 to the 12 Kelvin. I don't advise it. So experimentally, what they see, this was the summary on the right. If you collect this data in a lead-lead collision where I'm at 5 TeV per nucleon, then what you get is the black dots down here. When you look in the dimuon spectrum, you can see that there's no longer a peak sitting up here where the 3s used to be. The 2s is a little wiggle now, and you can see a 1s. But then you have to measure this relative to something. So we construct in this area something called RAA. So RAA is the ratio of the essentially the scaled up PP cross-section multiplied by the number of binary scatterings that are expected in the nucleus-nucleus collision. So it's sort of the null hypothesis that a lead-lead collision is just a bunch of nucleon-nucleon collisions, and I can just scale it up. That's this red curve here. And then the observation from the experiments is at least the fit is the blue curve down here. And as we can see, there's significant suppression of these excited states, and there's even suppression of the 1s state. Now, RAA itself is computed as just simply the ratio between the blue and the red curve. Now, in this case, they've collected all possible data, but you can bin the data as a function of the PT of the transverse momentum of the upsilon. You can bin it as a function of the centrality of the collision, rapidity, and all that stuff, and then measure these ratios directly. Now, in experiment, they measure these PP cross sections, so those become a reference. So you have to have these measured at this, basically the same nucleon center of mass energy as as in your lead collision or gold collision or whatever you happen to be colliding, and then you do this scaling, and then you report the observable. Now, on a theoretical side, as I said, the conceptual problem can be reduced to the following: that I have some quark-gluon plasma, and then inside of the quark-gluon plasma, I have some modification of the potential between the heavy quarks, but it's complicated by the fact that the imaginary part of this potential is not equal to 0 in here. And that means that in here, the evolution will be non-Hermitian. You won't conserve unitarity. Now, you can ask, well, how are you not conserving unitarity? That's a sacrosanct principle. Well, you're not conserving unitarity in the In the bound state channel, of course, those states go somewhere and they go into the unbound universe and into the quark-gluon plasma. And I'll discuss this in more detail. You have to take the system and divide it up into two blocks, the quarkonium sector and the rest. And it's only in that quarkonium sector you kind of have this non-Hermitian evolution. So because describing bound states, again, this is like a tiny little hydrogen atom. If I want to get the spectrum right, I can't use classical physics. I have to use quantum mechanics. Yeah, so I imagine that I have some quantum mechanical wave function. It can be in a linear superposition of all of these states. It can also have different angular momentum than what I've shown here. It can also have the unbound states, which are the color octet states, and truly like really unbound states. So there's some general wave function. I have to shoot it through my system, evolve it in time, subject to this complex valued potential, and then measure the wave function on the outgoing side. And of course, during this evolution, these coefficients are going to get modified. So I'll get a different overlap with the 1s on the outgoing side and on the 2s, and I call these A prime and B prime. And I can take then the modulus squared of A primed over modulus squared of A here, and that will tell me the survival probability of the 1s. I can also couch this in the language of the density matrix, where these probabilities are simply the modulus squared of these coefficients for each of the states in this expansion. And on the outgoing side, I get some modified probabilities for being in each of these states, at least the diagonal ones. Now, the reason that I can think of it in this sort of brick-like way is that bottomonium states are produced locally by very hard processes. They have masses of 10 GeV, so you need a gluon with 10 GeV or higher around to produce them. They're produced very early in the quark-gluon plasma lifetime. The 1s state, for example, you expect it's completely produced by around 0.2 Fermi over C after the collision. And then they're not produced anymore after that, and they just zoom through the plasma, and we can just have to trace their history. But as I mentioned before, the bound states can break up due to in-medium transitions caused by gluon absorption or emission. They can break up and they can reform. So we have a complicated quantum mechanical task here to understand. So the first thing I wanted to do was to have a kind of undergraduate level description of the first effect, which is the modification of the real part. So if I have just a normal electromagnetic plasma, and this analogy extends to a quark-gluon plasma, let's just focus on an E and M plasma because it's easier to draw. If I take a plus charge in an E and M plasma, the charges have been freed, so they can move around. And what will happen is the minus charges will be attracted to this free plus charge, and they'll screen out its interaction. So this was, something that was discovered, let's say, quite a long time ago. And the effect mathematically is that the potential that I would have in vacuum, in this case for electromagnetism, which is a nice Coulomb force, gets modified to a Debye screened force where there's some temperature dependent Debye mass, which is proportional to the coupling constant in the theory times the temperature, which turns off the interaction at long distances. So for distances larger than this Debye screening length, which is the inverse Debye mass, there's essentially no interaction between the quarks and anymore. Now, this effect is important for quarkonia, but it's also very important for understanding why we can treat the quark-gluon plasma as a sort of weakly coupled thing in the first place. Because in practice, G is not small. G at the temperatures that we probe in a quark-gluon plasma it's on the order of 2. But what's important is that there's always this screening effect going on, so that things that are well separated from one another do not couple strongly. So screening actually is one of the most important phenomena to understanding the quark-gluon plasma itself. Now, in the context of heavy quarkonium, we have to consider what would happen if we solve the quantum mechanical problem with a Coulomb potential or a Debye potential. So I've drawn that here. So the black line is the Coulomb potential, and the red dashed line is our Debye screened version of this. So so I can think of this as zero temperature is the black curve, and the red dashed is at finite temperature. Whatever that temperature is. I just made up some number for the plot. Now I can solve the bound state problem just by solving the Schrodinger equation in this case for the vacuum, and I would get some spectrum of states. Here this might be the 1s, the 2s, and the 3s states that I was talking about before, and then I can repeat that exercise with at finite temperature with the red one. And in that case, I would see that, well, there's some shift in the energy levels due to the fact that I had a different potential. And here I'm probably exaggerating it, but just to show you what exists. But I could also get states that go unbound. And so the states can completely disappear from the spectrum. So two things can happen. One, their energies shift around, and then if I reach some threshold temperature, those states can just disappear from the spectrum and go into the continuum. And that's why people in the 80s said, well, you know, this effect will cause, you know, some sort of breakup of the states, and it will affect the excited states first, because they're the first ones that'll get kicked out into the continuum. And then if I keep jacking up the temperature, eventually I'll destroy all of the states that are bound, and everything will become unbound. The second, so that's been understood for a long time. As I said, the second piece of the puzzle came when we found out that there was an imaginary part to the potential. Now you can go through the detailed sort of quantum field theory calculations of this. I will refer you to that original line of paper for the first demonstration of this. But I wanted to just go through a kind of heuristic way to understand how you could ever get an imaginary part to a potential. So how can we understand this without going through some complicated quantum field theory calculation? And the easiest way I know to generate this imaginary part is to consider your original problem, which was, you know, non-relativistic dynamics in some potential, but now I add some noise to the system. In this case, the noise is due to the environment. It's the light quarks and gluons and everything else that's flying around that is, you know, perturbing our potential. That here, well, actually, it's perturbing the quarks. So here, I can decompose this into some noise field that's acting on the quark and the anti-quark, and then I can ask what are the properties of these noise fields. So this noise, of course, it has zero mean. And at first approximation, you can assume that it's uncorrelated in time. So that it has some spatial correlation, which I won't even specify what the shape of it is. You can think of it as kind of a Gaussian, so that, or in your head if you like, but formally we don't even have to specify what this is. So mathematically, these are the statements that the noise averages to zero if I average over the noise fields, and then it has some correlation because it's uncorrelated in time. There'll be some delta function here, but then it has some spatial correlation, which is expressed in terms of this d. Right, so this is the setup. So let's imagine we had this kind of noise. I'm going to assume, in fact, that it's color neutral noise. You can add real color charged noise here as well, and you can also add correlations in time. But I won't go into those details. So let's just imagine this setup, that I had uncorrelated noise in time with a given spatial correlation function d, and I wanted to evolve the wave function forward in time. So normally I do that, right, with the time evolution operator. And if I expand the time evolution operator to second order here, expanding out this exponential, what I will find is in these parts, I will pick up, because H includes these noise fields, I will pick up quadratics in those noise fields at this order. Now the linear terms all go away because of this averaging to zero, but at quadratic order, interesting things can happen. And then I can ask, on average, so let's construct an effective Hamiltonian that averages over these noise fields. The first part here just contains the real part, and the noise fields average out, so you just get the normal kinetic energy plus potential part. But at second order in this expansion, you get these expectation values of the noise fields. And then we have to go back to our fundamental definition of these noise fields in order to see what's going to happen. And this is a continuum form of this delta function. If you write this in a discrete form, we're doing little time steps now instead of continuous updates. What you would find is that this is a Kronecker delta, and then for dimensional reasons there has to be a 1 over delta t hiding down here. So these correlation functions that you see here that appear at second order actually have a 1 over delta t that cancels this, and then these two terms actually become the same order. This term will become a correlator at 0 separation. This will be a correlator at 0 separation, and this will be a correlator at separation r. And so in the end, I can, there's a factor of 2 that comes out on all these two terms. It kills this 2, and I can write those terms that emerged from the things in curly brackets here as some modification of the potential. And these are purely real functions, this correlation function d here. And so you can immediately write down what is the imaginary part of this potential. Now, if you like to think of things in terms of the path integral, what this is saying is that, as I propagate through the quark-gluon plasma, I have some wave function, and there's a noise field, but I have to sum over all possible noises, right? And what can happen is that, and then I have to sum over that. And what can happen is that the wave function interferes with itself when you sum over all of these possible noise realizations. And that's encoded in this term in the evolution operator. Now, this is not how we do it in practice. Some people do it. For example, Alexander Rothkopf and company and Akamatsu in Japan, they have this sort of implicit idea that you have sort of noisy quantum mechanics. I'll show you a different way of getting to having an imaginary part of potential. But this is, I think, the easiest way to sort of understand, well, how could I ever get one in the first place? You have noisy quantum mechanics. It just emerges naturally. The way that we're going to approach the problem is slightly different. We're going to formally use what's called an open quantum system approach, in which we take the entire system, this is our quark-gluon plasma, and we're going to divide it into 2 bits. First is our heavy quarkonium state, which we're going to call the probe, and then the medium, which is everything else. Of course, if I take the whole system into account and I look at the evolution, it's going to be unitary. But if I look at just the evolution of the probe or the medium separately, there's no reason that they individually have to be unitary evolutions. Only when I sum over both bits does that have to be true. What we're going to do then is take this total system, and we're going to integrate out the medium degrees of freedom, and we're going to obtain an effective field theory that only describes the probe degrees of freedom. And that's sort of shown down here. So formally, what we're going to do is take the total Hamiltonian, we're going to decompose it to a probe piece, a medium piece, and of course, there's still interactions between the probe and the medium, otherwise it wouldn't be interesting. You can treat these interactions perturbatively, or in our case, we're going to treat them using potential non-relativistic QCD, which I'll describe what that is in a few slides. If we were taking the total density matrix, as I said in words, we would know how to evolve it. We would just get an evolution equation. This evolution equation conserves rho, because if I take the trace on the left and the right, this is a commutator, and the trace of this commutator is going to give me 0. So the time derivative of the trace of the total density matrix in this case is 0. So that's the conservation of probability. If I integrate out these medium degrees of freedom and I only get the density matrix for the subsystem, that's schematically indicated here. In general, you get something called a quantum master equation. And typically this was, sort of condensed matter territory, let's say 20 years ago. For example, Anthony Leggett won a Nobel Prize for deriving these kind of quantum master equations. Now, the kind of quantum master equation that you get out on the right-hand side depends on the scales in your system. And you have to compare various scales. In the worst case scenario, this quantum master equation is non-Markovian and horrible and almost impossible to solve. But there are cases where you can reduce it down to a Markovian evolution. And in the case that it's a Markovian evolution, you can always map that quantum master equation to something called a Lindblad equation. So first I have to describe what is that limit physically, and then we'll try to connect to QCD. So in the middle of the slide, this is a general statement. So this would apply also to condensed matter systems, atomic molecular systems, where you're applying this open quantum system kind of idea. And when you analyze these systems, you find there's three relevant timescales. One is the medium relaxation timescale. So that's how fast does the system itself, like in this case, the quark-gluon plasma, the light degrees of it, relax back to equilibrium after I perturb it with my probe. And in general, that's given by some expectation value of just some correlator between two medium operators. And in general, that, at least in the high temperature limit, this is going to be proportional to 1 over the temperature. And that's true in the quark-gluon plasma. If you look at quark-gluon plasma, the relaxation time for non-equilibrium deviations in the quark-gluon plasma at high temperatures, it goes like 1 over the temperature. So the higher the temperature is, the faster it relaxes back to equilibrium after some probe goes through it. The next time scale that you have to worry about is what's called the intrinsic probe time scale. And that's related to the level spacing in the system that you're considering. So if this was an atomic molecular system, this might be a 2-level system, and this would be the spacing between the 2 levels in the system. That defines another time scale for transitions between these levels. In the Coulomb case, this is the level spacing in our upsilon 1s spectrum. And parametrically, this is given by 1 over the binding energy of the state. The last time scale that you have to worry about is the probe relaxation time itself, right? So you have a probe, you have some plasma shooting through there. How long would it take to turn that probe by 90 degrees? How long would it take to equilibrate it? So that's what this last one is. And the nice thing about heavy quarkonium is because it's so heavy, it takes a very long time for them to equilibrate. So this time scale is quite long, and you can estimate what it is. But what emerges, at least in the high temperature quark-gluon plasma, if we're looking at temperatures on the order of, let's say, 500 MeV, is that there's a strict ordering of the scales where the inverse size, so these are very small states, so this is actually a large scale. It's much bigger than the temperature. And those two, and which is on the order of the Debye mass, these scales are not well separated in general, but that's also, these scales are much bigger than the binding energy. So the binding energies go down as you're sitting in the quark-gluon plasma, and at these high temperatures, this hierarchy will be obeyed. And what that translates into is that these two scales down here, the intrinsic probe time scale, which I call TP, and this probe relaxation time scale, tau relax here, are much greater than the medium relaxation time scale. And this precisely gives you this Markovian limit, which means that after my probe has passed through, the medium relaxes back to equilibrium super quickly and forgets that there was even a probe propagating through. So that's what results in this Markovian evolution. And there's a general statement, as I said before, in all open quantum systems in which the evolution is Markovian, you can always map this quantum master equation into something called a Lindblad equation.
Sorry, I have a question.
Yeah.
when you're dealing with these open quantum systems, we sort of naively, we really care about the time evolution of the probe. So is the only time evolution of the medium that we're considering this medium relaxation time, which we just sort of approximate to be one at the temperature?
Yeah, so no, we just try to estimate what this is. In practice, as you're going to see phenomenologically, we use some hydro code to do the medium evolution. The hydro code itself has relaxation times like this, but we don't try to track the perturbation. So you could try to go one step further where you were shooting your quark-gluonium through, they perturb the hydro medium, and then you functionally look and see how fast this relaxation time. But what I'm going to show you today is because we know that internally the relaxation times are 1/t, we just ignore the back reaction and the medium relaxation itself. But okay, you could try to do that, but it makes the problem even harder.
Thank you.
Yeah. So yeah, we're just going to assume that this is fast enough that we don't have to worry about keeping track of the fact that the quark-gluonium just went through. Now, the other reason that this is a valid thing to do is because the bottomonium states are so rare. It's not like you're going to have another bottomonium state coming right after this one, right? They go through. Maybe the medium, is relaxing in its wake, but it's not like it's going to circle around and go back through. It's going to keep going, and there's not going to be a lot of partners following it. Good. So in this case that you have a Markovian evolution and the medium relaxation times is sufficiently fast, you can always write this evolution equation in this form. The first term looks like our old friend, a commutator between the Hamiltonian and the density matrix, but then you get these additional contributions where these operators here are called jump operators or collapse operators. People call them different things in the literature. But if you take the trace of this thing now, this term vanishes, obviously, and then these two terms actually cancel against one another. So in the probe sector, we now have a manifestly unitary evolution. And that's because in the probe sector, we're going to keep track of both the bound and the unbound states. So we're going to, within this sector, we've now been able to construct a unitary evolution. There's still a complex Hamiltonian hiding in the problem, which I'll show you in a few slides. What these jump or collapse operators encode are these internal transitions between the different energy levels in the system. So there's one operator for all possible transitions that you can make. If this was a two-level system, these would just be raising and lowering operators, sitting here that allow us to go from, the ground state to the excited state and back. In general, these can be some complicated operators that you have to determine through a calculation. So the way that we're going to compute these jump operators here for our specific case is by using a sequence of of effective field theories. We start with QCD. We have some very heavy quark or bound state in this case, or M here. And I can integrate out this scale M to obtain something called non-relativistic QCD. There's a next scale down, which is the soft scale. If you know anything about hard thermal loops, this would be GT, but now it's V times M, where V is the small quantity that we're dealing with here, not G. And then there's an ultra soft scale, which the analogy again would be G squared T. Well, this is now V squared times the hard scale. So it has a lot of analogies to hard thermal loops, which is why it was somewhat easy for me to segue into this. You have in the limit, in this non-relativistic limit, V becomes the expansion parameter. It's small, and you have a large separation between these three scales. If I continue to integrate out the soft scale, this one, which is associated with the inverse size of my bound states, I can then get it down to a Lagrangian that's written solely in terms of the singlet and octet degrees of freedom. I'm just going to show you, without going through all the words that are written here, what this looks like. So the non-relativistic QCD Lagrangian was, first worked on in the late 80s and then and continued in the 90s. And these are only, two of the papers. There's lots of papers out there and people that are probably offended in the audience right now because they didn't cite their paper. But what you do is essentially an expansion in 1 over the mass. So if you look at all of these terms, you'll see that there's a 1 over the mass appearing here. You're doing an expansion in V, essentially, or you can actually in this case it's 1 over the mass, and you can write down a complicated looking Lagrangian where these new spinners are the top part of the Dirac four spinner and the bottom part of the Dirac four spinner. They're the heavy and light parts of the Dirac four spinner in this limit. Now, in potential non-relativistic QCD, you start with this now complicated looking Lagrangian, and then whenever you have some 4 fermion interaction, you're going to integrate that out into a kind of point-like interaction between those guys and some Wilson coefficient, which in this case turns out to be the potential. And I don't want to go into all the details here, but suffice to say what you end up with is a Lagrangian in the end that looks like this, where you have the gluonic sector here, but then the degrees of freedom that remain are the singlet QQ-bar state, so color anti-color, and the octet QQ-bar state. The singlet has an attractive potential in leading order in this expansion. You just get an attractive Coulomb potential where you just have to adjust for the fact that you're in QCD by multiplying out the coupling constant by the Casimir and the fundamental representation. Then you also get from this calculation the octet potential, which has a plus sign. It's a repulsive potential. But these just fall out of the calculation. You don't have to put them in by hand. You just start with QCD, go to NRQCD, then integrate out the next level, and this just falls in your lap. The other thing that falls in your lap is are the interactions now between these fields. So I can have interactions between the octet and the singlet, which are encoded in these 2 terms here. And I can also have interactions between the octet and the octet. Now, this is the leading order version of this Lagrangian. You can work harder, and people have over the years to write down the higher order terms. Yeah, go ahead.
Just understand notation. E is really a color electric field. There's no color.
Yeah, E is a color electric field, and because we can assume that these states are small, these are dipole-like transitions. I thank you for making me say that out loud. Dipole-like transitions between singlet and octet. So this is just a chromoelectric dipole transition operator.
Mm-hmm.
And diagrammatically, we can start to draw diagrams where a single line means I'm coming in as a singlet, a double line means I'm an octet, and I either absorbed or emitted a gluon in this process, right? And that interaction, you just replace it by this chromoelectric dipole interaction. And likewise, I can do the same. I can have octet going to octet, through this line of the Lagrangian. Now, that allows us a great simplification because we no longer have to work with the QCD Lagrangian directly. We can work with this Lagrangian, and we can start drawing Feynman diagrams out with this Lagrangian instead of QCD. What this bottom panel is showing you is some part of how we calculated these jump operators here. And to calculate those jump operators, what you have to calculate is the self-energies for the singlet and the octet propagation. Because it's out of equilibrium, you have to use something called the Schwinger-Keldysh formalism. So these little 1s and 2s are labeling which part of the Schwinger-Keldysh contour you're on. And these graphs are just nice self-energy graphs, and they're sort of like a Schwinger-Dyson equation, if you like. This is the resummed propagator. This is the first part, and then you can see it. If you take these diagrams and you cut them, then you get these. Take the imaginary part of the self-energy, you get the transition probability, for example, like singlet going to octet, or in the reverse, octet going to singlet. So all of that information about what those jump operators is contained in the real-time quantum field theory formalism for the self-energy of singlet and octet states in pNRQCD. And if you're interested in the details of how that calculation goes about, I'll refer you to these two papers from 2016 and 2017, where they worked out all the details, at least to leading order in the binding energy over the temperature. So once you do this, you can calculate these jump operators that appear here uniquely. Good. I'm going to show you what those look like in a slide, but first I promised that there was going to be a connection to this non-Hermitian effective Hamiltonian stuff, and that we're going to make use of this when we solve this equation numerically. So I want to talk about it now. So this was my general Lindblad equation. Let's presume I know how to calculate these. I'll show you what they are. We do know how to calculate them. And what they physically correspond to, if you look at this particular combination, Cn dagger Cn, it corresponds to the partial width for the decay of my state in the nth channel. What does decay of the state mean in this context? Let's assume that I started with a singlet 1s state, which has angular momentum 0, and I had a transition to an octet state with L equal to 1. Again, there's selection rule here because it's a dipole transition, and I also have to change the color because the gluon had color. So that's one possible loss channel, is the singlet to octet transition. So that's going to be one of these jump operators. If I sum over all possible transitions that can occur, that gives me the total width of the state. And for singlet, if I started in singlet, there's only one. But if I start in octet, there can be, I can go up in this way, I can go over there. If I started in a singlet with finite angular momentum, actually, I do have more than one option. I can go this way or that way. I have to sum over both of those possibilities. So that's what this sum is. And if I stare at this term, that's exactly what I have. I have a sum over all possible transitions times the partial width, and then there's a funny factor of half here. But because of that, I can just reorganize this Lindblad equation at the top slide into the following form, where I now have a non-Hermitian Hamiltonian evolution with the total width operator sitting here. This probe thing is purely real. And then I get something that would look like my commutator term, but now because the Hamiltonian is non-Hermitian, there's an H dagger here, and H dagger is not necessarily equal to H. And then I have this leftover term that's sitting here. The interpretation of these two terms are that this is the loss of unitarity that you would get if I were to just evolve with this red term, let's say a singlet state, because the H effective is non-Hermitian, I would be, leaking out of this state. This is the term that restores these things, and it encodes all of these transitions between the different states. So we call this the jump term. So this is the rate at which I'm leaking, and then this is the jumps that restore sanity to the system and allow us to have a unitary evolution, or a trace preserving evolution in this language for the density matrix. Now we're going to exploit this separation to actually solve the Lindblad equation numerically, but I just wanted to show you that, yeah, there's this non-Hermitian stuff hiding in here. If I ignore this, which is what you would do in that kind of noise picture, if you ignore this term, it looks like a non-Hermitian evolution. But you can do better. You don't have to throw away this term. You can keep track of it. All right, so I can't show you all the details of the calculation. Again, they're contained in these two papers in 2016 and 2017, at least to leading order. And then in 2022, we went to next to leading order in the binding energy. So that's this paper. I'm just going to show you the leading order results on this slide, and then I'll briefly flash what it looks like at next to leading order just to show you that you can do it. So you go through, you calculate these self energies, you take the imaginary parts of them, and then those give you these operators. If you decompose the density matrix that's hiding here into a singlet and octet piece, then you can write these jump operators as like 2x2 matrices. And if you look at this one, if I come in with a singlet state, which would be a two-dimensional vector 1, 0, it's going to turn it into an octet state. If I come in with an octet state, it's going to turn it into a singlet state. In this one, if I come in with an octet state, which is 0, 1, it's going to turn it back into an octet state. So this is these guys are encoding the octet transitions, and these are encoding both the singlet octet and octet singlet transitions. And there's 6 of them. So this sum here sums over the 6 possible operators, and I here is going 1, 2, 3 in both of these cases. You can just do some math by summing over all of those jump operators after you've determined them, and then you can come up with this total width operator in this case. And so then you know how to construct this effective Hamiltonian. And it will depend on whether you're currently a singlet or currently an octet. So you get a different width depending on the color state that you happen to be in at that moment in time. And as we can see, there's some coefficient that pops out here, which we've labeled as kappa. And if you go through the calculation, what you find out is that kappa is related to an anti-correlator between 2 chromoelectric fields in the medium. Actually, these tildes are a shorthand notation. There's actually some Wilson lines sandwiching each of these things, but if I put the Wilson lines, it gets too big to put on the slide. So I just wrote that down here in tiny little font. So there's some coefficient, and the nice thing about this is a thing that you can measure on the lattice. And to leading order in the coupling constant, this is nothing but the single heavy quark momentum diffusion coefficient. So there's a tie-in here between the bound state evolution and the evolution of the single heavy quark in the system. There's another transport coefficient, which is the dispersive analog of this, where instead of anti-commutator between these 2 chromoelectric fields, I have a commutator between the 2 chromoelectric fields. That one's called gamma. And if you work through the details here, what you'll find is that at leading order in the binding energy over temperature, this gamma just pops out and gives us a modification of the real part of the Hamiltonian. You can think of this as that mass shift. Remember in the Debye screening picture, I said, oh, you can get a shift in the energy levels. This is that shift in the energy levels. And this is the width. This is encoding that imaginary part of the potential because gamma comes explicitly with an I. So this becomes the imaginary part of the potential. This becomes the mass shift. So now we have both effects included. We know what these jump operators are. We know what this effective Hamiltonian is. The jump operators tell us how to evolve the system when we absorb or emit a gluon in the system. And it can do a complicated dance between all possible angular momentum transitions as long as you go in steps of 1 and all possible or allowed color transitions. Now, if you work harder, and that's what we did last year and put out a paper that's now in JHAP in May of 2022, you can extend all of those jump operators to next to leading order in the binding energy over temperature. This is important because the binding energy over temperature actually turns out to be not a small number as you go down in temperature. So if you want to do phenomenology, you also need to worry about these subleading terms. Of course, you might want to worry about also the next to leading order terms, but you can only do one thing at a time. So we went to next to leading order there. Once you know these jump operators at next to leading order, you can write down the new effective Hamiltonians, and it works exactly like at leading order. So we can evolve with some non-Hermitian piece, and then we have these jump operators that are connecting the states with different quantum numbers, L, and their color quantum number, which I call seek. Good. What about these transport coefficients? It turns out they can be measured, as I said, on the lattice. And I'll focus, I think I do both here. So this is a paper from 2019 from Larson and company, the group at BNL, where they use non-relativistic QCD, but now put into a lattice calculation to calculate the widths, in this case of the upsilon state, as a function of the temperature, and also this mass shift as a function of the temperature. And one of the surprising things that came out of this calculation is that, well, we expected there to be a width. Their width is quite large, but based on, I guess, perturbative expectations. But you can use this now as input. By measuring the slope of this line, you can infer what is the value of this transport coefficient kappa at all temperatures. The surprising thing was that they saw no mass shift whatsoever, right? And what that implied was that this other coefficient here, gamma, which is sitting here in this mass shift, is actually very close to, if not zero. So we can use this information as a kind of starting point. You can say, well, what is the value of kappa just by looking at this lattice data? We expect that gamma is going to be small, if not zero. And they also found the same thing in the L is equal to 1 states. These are the chi-B states, and very little mass shift up to at least 400 MeV. It's consistent with zero. So this, if true, and nobody has proven that they've done something wrong here, this means that essentially the old Matsui-Sachs picture has been thrown out. There is no Debye screening. There is no mass shift. It's all in the width. And but because we have a theory that can now include both effects, we're good. All right, so, go ahead.
So for that value of gamma, if I'm remembering correctly, gamma was also tuned the parameter that prevented non-unitary evolution. So if our gamma is very close to zero, are we not?
No, the fact that you have a unitary evolution is independent of the values of gamma and kappa.
Okay.
When you sum over all three terms here in the probe sector, yeah. So I mean, this is the thing that, yeah, if this in these two terms, when kappa is non-zero, you have non-unitary evolution. This term always gives you unitary evolution. You have a real Hermitian Hamiltonian here, even with the modification from the mass shift. It's this term that would blow unitarity in these two terms, but in practice, we don't throw out this last term. So the whole evolution turns out to be unitary. And that's because these jump operators are keeping track of where the things that decayed actually went. Yeah. Loosely speaking.
Okay, yeah.
Good. So when I first entered this game, it was upon invitation from Nora Brambilla and company in Munich, because they wanted they had this at leading order and they wanted to solve it numerically. But what you find is that if you start just thinking about this as solving some time evolution of some very large matrix, right? That's what the density matrix is here. You would, continue this process of splitting out your density matrix. So you would then decompose the singlet part into different angular momentum parts and the octet part. And so then it becomes an even larger matrix with some truncation and angular momentum. And then for each of those, say L is equal to 0, within the singlet, there's a sub-block, right? And each of those would then have to have, let's say, 1,000-point wave function living on it to describe the spatial variation of the wave function. So very quickly in this game, you get to matrices that are, 10,000, 100,000 by 100,000. And this becomes very, very hard to solve numerically if you try to think of it in this naive kind of matrix way. So that's what I wrote here. You can decompose it into color space. In addition, that's what we did first. And then we decompose it into angular momentum blockwise. You truncate that. Then you have to discretize the wave function. You get some big matrix size, and you'll find that this even multiplying these two matrices scales like the matrix size cubed. You can get it down to roughly 2.5 if you do, super optimization of the problem and get lucky. But eventually you won't even be able to fit this in your memory. Never mind evolve it in any reasonable amount of time. So we needed a better, faster way that we could parallelize the solution of this equation. And we didn't invent it. We stole it, in this case, from condensed matter and optical physics people. So there were papers going back to the late 90s, early 2000s, where a method called the quantum trajectory method was introduced. And you use this split that I introduced earlier. So the idea, and I won't try to describe it in equations, but I will describe it in words and pointing at this picture. So what I do is let's say I started in a singlet state, which was an upsilon 1s. So L is equal to 0, singlet state. I pick a random number between 0 and 1. Let's say that number was 0.5. I then evolve using the blue term here until the norm squared of my wave function drops below 0.5, because this is the non-unitary evolution. When that happens, I trigger a jump. So then I jump over to this term and I say, well, I need to now jump to a different state. But I don't know which state necessarily. Let's say in this case, I know which state I have to jump to. There's only one possibility. But in general, if you were in somewhere in the middle, there might be multiple ways for you to jump, right? And so then you have a second random number or set of random numbers, which tells you which of these jump operators to trigger. Once you've triggered the right jump operator, again, this is chosen randomly, like in Monte Carlo evolution, I merge into my new state. I then reset the norm of the wave function to 1, and then I start evolving with the blue term again. I generate another random number. I wait till the jump is triggered, and then I pick a jump operator, and I might go up here, I might go down. And I just repeat this over and over and over and over and over again. Now, the great thing about doing it this way is that you don't have to actually decompose this into angular momentum blocks. And this algorithm, most of the time, you're just solving for the time evolution of the wave function in some non-Hermitian Hamiltonian that scales linearly with the size of the wave function. So instead of having something that's scaling like this, the size of the density matrix cubed, you just have something that's n cubed. You have now just n. So anytime you can do that, that's great. We don't have to truncate in angular momentum then, because at any moment in time, I'm in a given angular momentum state. So I don't have to, in essence, this space is infinite. So I don't have to truncate in the angular momentum state. And each of these trajectories is independent. So imagine that I had some, and I have a picture of this on the next slide. I have some state that's shooting through here. I can just evolve each of these possible quantum evolutions along that physical path completely independently. I can fire up 1,000 cores. Each one is just fed a different sequence of random numbers. Those random numbers tell me, the dance that I do in this singlet octet space here. And then I just average, right, over all of those realizations of these quantum jumps. So this turns it into an embarrassingly parallel thing. If you have 1,000 computers, you can run it 1,000 times faster. It scales perfectly. So that was the breakthrough that occurred in 2020 was, we stole this idea from other people. They usually didn't apply it to situations with such large Hilbert spaces, but we did. Right, and now you have to apply it to phenomenology, and now comes some old-fashioned heavy ion physics. So the first thing you have to do is sample the production points for these bottomonium, and in the calculation we oversample. So normally you would only produce one of these, maybe two of them, but what we do is we sample 100 of them. We sample their initial production points from the binary collision overlap of the two nuclei. So this is a particular non-central collision, and you'll produce them here sort of probabilistically aligned with the shape of the quark-gluon plasma itself. And then, of course, we also sample their momentum. We sample their momentum from essentially the PP production cross-section, so we know what to sample there. And then they will evolve in time, but the quark-gluon plasma will evolve in time. For the quark-gluon plasma evolution, we have a code that I developed here at Kent State called 3+1 dimensional anisotropic hydrodynamics. It's been fit to all sorts of soft hadron data, so spectra, elliptic flow, all of that stuff. So this we can just use out of the box. There's nothing to tune there. And then we just shoot these guys through, and along each of these physical trajectories as they're following, moving along their physical trajectory, we just solve this Lindblad equation by averaging over all these possible jumps using this quantum trajectories algorithm. And for each of them, we then calculate their survival probability, which is as I said earlier, the ratio of the final overlaps of a given quantum state I'm interested in with the evolved wave function now evolved through this complicated non-Hermitian plus jump operator bit, and then I just have to divide that by whatever the initial overlaps are, and that gives me these survival probabilities. So at the end, I don't show the last bit, but the quark-gluon plasma is essentially gone, and you just have these states flying away. We're able to calculate their survival probability, but there's one more piece that you have to include for the phenomenology, and that is that at very late times, let's say that this state wasn't an upsilon 1s, but a chi b1, so a 1p upsilon state, which we also simulate. Those things can decay down to the 1s. So but that occurs at a much longer time scale than quark-gluon plasma. Quark-gluon plasma lives 10 to the minus 22 seconds. This is happening on a time scale of like 10 to the minus 14, which is still short, but it's orders and orders of magnitude longer than the quark-gluon plasma lifetime. So you can factor these two pieces into separate bits. So at late times, you just have to apply some feed down matrix. So you get some vector of survival probabilities for all of the states that you've simulated. You just have to feed them through some matrix that tells what is the probability that these decayed into the various different states. That information you can just get from PP collisions. These numbers are just read out of the PDG. We include the uncertainties. The table was too big for me to put all the uncertainties, but you can just read this out. So this is not some new theoretical ingredient, but it's something you have to do. Why do you have to do it, right? Imagine if it were the case that let's say that this chi b1 like really decayed a lot into the upsilon 1s, then there's a chance like all of like a half of upsilon 1s, for example, might come from production of this state, because they just like to decay there. And if you were in the quark-gluon plasma and you killed all of these, well, they can no longer decay down to the 1s, so that would mean that you would get a 50% RAA just by killing the 1p. So you have to be very careful in this game. So in practice, what we do is we take the direct production cross-sections in PP, we then compute the survival probability in a given observable class C, we then attack it with this feed down matrix. divide by the experimentally observed cross sections in PP, and that gives us RAA. If we didn't have a quark-gluon plasma, this S would be 1, and by definition, this ratio turns out to be 1. All right. So long-winded story of how we actually do this. There's lots of, there's hydro, shooting things through the hydro, thousands of machines working in unison in order to calculate along each of these physical trajectories the survival probabilities, and then we can compare to the data. Finally, good. So what's plotted here is from a paper in February of this year, where we've now gone into this next to leading order formalism. The horizontal axis is what's called M part, which is a measure of the centrality. Over here is a glancing collision where, we expect maybe not to, eventually at 0, we don't make the quark-gluon plasma. And over here is where we make the hottest, longest lived quark-gluon plasma. And the vertical axis is RAA, now on a log scale, because these excited states, as it turned out, are so suppressed that you need a log scale to resolve them. And there's experimental data. Luckily, we're getting data from ALICE, ATLAS, CMS at at least 3 experimental stations at this point, and the experimental data is consistent within the error bars or uncertainties that are reported here. And then we have some model predictions, which are here from solving that Lindblad equation. And we did 2 possibilities. One is the dashed. That's when we just did the non-Hermitian evolution and we ignored this jump term. So we just evolved it with a non-Hermitian Hamiltonian and just turned off this jump. And in the paper title is called quantum regeneration. So why does that mean that we don't have regeneration? If we turn off this term, we don't have quantum regeneration. What is quantum regeneration? Quantum regeneration is that I can go through this dance and I can break up the state, but that at a later time I can reform it, right? And that will only happen if you turn on this jump operator. Otherwise, I just lose. So that's what's shown here between when you compare the dashed to the solid curves is what happens when you turn on this jump term in the evolution. The value of the transport coefficients, we actually did a sort of phenomenological scan. I'll show you, sort of fit plots in a slide, but it turns out it comes out very consistent with the lattice data that suggests that there is no mass shift, and there's a quite large width for the states. There's 3 different states here. There's the 1s, the 2s in this orangey color, and the 3s is the green that's sitting here. And what you can see is that for the 1s, there is an effect from this jump. I would say that both are consistent with the data. But when you start looking at the excited states, this becomes very important. You have to include this possibility of quantum regeneration of the states, not just that they break up and never come back. So in practice, what we did was, repeat this calculation for various values of these transport coefficients, gamma hat and kappa hat, with jumps and without jumps. That's the width on the top and without on the bottom. And this is my sort of summary of that. This is without the jumps. This is the best fit for the 2s is in this region of the parameter space, and the best fit for the 1s is this region. And as we can see, there's no overlap. You can't simultaneously describe the ground state and excited state overlaps without including these quantum jumps. But once you include them, you find that, okay, there might be a disconnected region over here, but there is a nice region where there is an overlap. You can simultaneously describe the 1s, 2s, and it turns out the 3s at the same time. That was this figure here. So, and the good news was that this overlap regions is largely consistent with what they're seeing on the lattice. Now, when we sample things, not only do we have the hydro, for different impact parameters, which are the centrality, we also have different transverse momentum upsilons. Remember, the transverse momentum was sampled from the underlying PP production cross sections. So we can also compare to data that's collected as a function of the transverse momentum. And once again, you find that, well, for the 1s, maybe this is within the error bars, but for the 2s, it's clear that you really have to include these jump operators in order to get close to the data. Another thing that experimentalists measure in this area is the ratio, what they call the double ratio. Essentially, it's the amount of 1s suppression relative to 2s, or 2s relative to 1s, and 3s relative to 1s, or 3s relative to 2s. And the reason they like to do that is it cancels some experimental uncertainties related to their acceptances. So they also report these double ratios. And here, once again, no jumps, jumps, no jumps, jumps, no jumps, jumps, no jumps, jumps. So and these are very nice observables because the error bars, we're not on a log scale. This is linear, and the error bars are quite small. And if we integrate over all possible PT and all possible centrality, then we can come up with summaries for each of the states and summaries for these double ratios. And the QTraj, or our Lindblad solver, are these little round circles on this summary plot, and the world's collected data are the things with error bars. So we were quite pleased with this result. Since then, in May of this year, together with a student here at Kent State University, we went one step further. Here, in this paper from February, we were only sampling the transverse momentum, but there's another dimension in heavy ion collisions, the rapidity direction, which is coming out of this slide. So these guys can also be flying towards you and back and into the slide away from you. So what we did was then include that, because the hydro was fully 3D. We could then include this now full three-dimensional evolution. And what we found was that we were still able to describe the data. In fact, we were able to describe it even better once we included the rapidity dependence. And we were then also able to make a prediction for the rapidity dependence of this suppression, which you can see from the experimental data is quite flat, at least up to rapidities on the order of 3, and it seems consistent with our numerical calculations. Now, there are these 3 points hiding here from Alice, which seem to be, let's call it tension. That's what we like to say in heavy ions when things don't agree with the data exactly. There's some tension here. And we're working on fixing this. I believe this is what people call cold nuclear matter effects, or nuclear modifications of the nuclear parton distribution functions that occur at very large rapidity. But in the central rapidity region, we seem to have a quite good description of the data, and also improves our description of these double ratios. Now, not only can you get RAA out of these calculations and also experimentally get RAA, you can also measure the V2 of upsilons themselves. And I'll go very quickly through this. The reason people are interested in V2 is because if you look at the J psi, what you see, if you measure its V2, which is the differential production, how many more are produced along the short side of the overlap than going along the long side. And what you see is that there's a sizable V2 for the J psi at 5.02 TeV. And what this implied to people is that the temperatures are now high enough that you're thermalizing the J psi and they're flowing with the medium. But when they did the same measurement for the 1s, the error bars here are admittedly quite large, but it was consistent with 0. And as a function of time, these error bars are just going to get smaller and smaller. And there's 2 curves here, which were where our predictions before this was actually was measured by myself. I'm the S in BBJS, and there's Tamu, which is Ralph Reps, and we basically made the prediction, both of us, before the data came out, that these guys won't flow. And now, using this same quantum trajectories algorithm, we can, measure this quite precisely as a function of centrality, if you like, and both for the ground state and the excited states. And then if you integrate overall, so this is sort of the min bias, so you don't care what the centrality was, you integrate over all possible PT, we have very precise, or let's say statistically precise, at least predictions for how big this flow should be, and the answer is 1%. And so far, it's consistent with the world's data. We'll see what happens in the future. But if this holds up, what it means is it's great because the upsilon is not thermalizing. If it did thermalize, then it would forget all of the history of its passage through the quark-gluon plasma. It would just be another, part of the mess that comes flying out. But we can now preserve history by the fact that this thing doesn't thermalize. All right, with that, I have no concept of the time because I don't have a clock. I'm going to conclude. So in the first part last week, I tried to show you that, there's this quark-gluon plasma. There's lots of things that you can observe. In the second one, I wanted to focus just on quarkonium and how starting from the sort of cartoon pictures of quarkonium screening in the quark-gluon plasma, turn this into a real quantum field theory calculation where you start from QCD, you do a lot of hard work, and then you can describe the data. So that was the first statement here, that we have now made the first fully 3D quantum non-abelian treatment of quarkonium using effective field theory and this open quantum system approach. In the last year, we've been able to extend that to next to leading order. We can constrain the transport coefficients by lattice measurements. We can also constrain them experimentally, and then we can see, are these two things consistent? Functionally speaking, we seem to be able to describe the end part, the PT dependence of RAAs, the double ratios, and also the flow. So I would say that things are looking quite good. All of this relied upon finding a clever algorithm to solve this Lindblad equation. If you're interested in this stuff, you can go to the papers. This code is an open source package. You can just download it and start playing with it. If you want to make improvements, run it through a different hydro model, you can do that. And if you need any advice on how to make all that work, I'm here to help people. And then finally, in the papers that came out in February and May of this year, we showed that there's this effect of quantum regeneration. Even if you only had one upsilon 1s state, or let's say one upsilon 2s state shooting through the quark-gluon plasma, you have to take into account the fact that it can break up and then reform at a later time, and we're calling that quantum regeneration. All right, with that, I will end and open for questions.
Thank you. That was actually fantastic. Yeah. I mean, if you need an impressive demonstration that unitary actually does matter, this is one.
Yeah, well, I mean, there's always, well, we're working hard to include other things, and people, I don't know, there's a law in physics where you should stop once you agree with the data, right? And you should stop adding things, right? Because you're going to break it. But and so we may break it going forward, but things like going to next to leading order in this expansion, including more realistic and non-Coulomb like effects and the potentials, there's still work to be done. I don't want to sort of imply that it's over.
So that actually gets me, well, no, you guys ask your questions first. I reserve mine for later.
Yeah, I just have a basic question.
Yeah.
When you got the Lindblad equation, you emphasized Markovian, and has static Markovian, and that the previous equation was non-Markovian.
Yes.
Could you maybe explain what it means for it to be Markovian, why it's important that it's Markovian?
Yeah, why it's important is Markovian well, yeah, so it's just a practical consideration, because if it's not Markovian, it becomes much harder to solve numerically. So when it becomes Markovian, it becomes this Lindblad kind of thing. You can just very easily apply this quantum trajectories algorithm and have a perfectly scalable algorithm to solve it. Once you break that, it becomes much harder to solve the quantum master equation evolution. Now, there are tricks out there in the literature, but it just functionally becomes much more difficult. It's doable still, but yeah, more difficult.
Okay, sure. Thanks.
And there you would also, as I discussed earlier, you would have to keep track of, the response of the medium. Right now, our hydro, we just run it, we export it to disk, and then we shoot things through it. We would have to be like running the hydro at the same time we're shooting things through it, and like keeping track of all the perturbations, and then solving a quantum master equation on top of that mess. So yeah, it becomes practically difficult. But yeah, as I said, you could do it.
Okay. Thanks.
Right, I have two questions. So the first one is, when you calculated the survival probability from the hydrodynamic model, intuitively, something that was created sort of, I want to say, in the center of the plasma has a lower survival probability than something that's created on the periphery.
Yes, that's correct.
So when you actually did a sampling, was it I assume when you did sample, you applied some weight to say, there was a certain amount created on the edge and a certain amount created in the center? Or...
Yeah, what you expect is that you're going to create upsilons with some probability where there are pp collisions, right? And in the center of a nucleus-nucleus collision, there's a larger number of pp collisions that can occur because you just have a longer path length, right, to go through. If you imagine the squished pancakes, there's just a higher probability for generating the guys in the center than in the edge. And this you can compute from what's called the binary collision profile. So I don't have a 3D picture of it, but it's peaked here in the middle, and then it falls off as you go to the edge very quickly. And then we sample from that. So this is just one realization of that sampling. This is sampling a bunch of them, 100. I don't remember the number that I threw here. But yeah, it's extremely rare to produce one out here. It does happen. It's more probable to produce them here. But yeah, we do this over and over and over and over again, sampling them. And you're right, I had some pictures of essentially this survival probability as a function of where you started. And these guys in the center, they just get killed. And the guys that got sampled out here on the edge, those are the ones that survive. And so you have to do this over and over again, and then average over this entire ensemble.
Okay. Okay, yeah, and what we see in the slide there is then the average of the entire ensemble. Okay.
Yeah. So yeah, when I do this, I've now averaged over all of those sampled physical trajectories. Yeah.
Okay. And then the second question is, do you have a good idea of why the more excited states need quantum regeneration compared to the less exciting states? Because it's quite a dramatic effect between the two.
Yeah, I'll just be honest and say no. We have some hypotheses, and I need the figure to point at. So it has to do with the number of paths that you can take to get back to this state. So and the number of jumps you would have to apply. So in the beginning, you have a high probability of being in the 1s state. The first jump that you make will be to an L is equal to 1 octet state, but then you could jump over here then eventually you have to find a way to get back to a singlet state, but that's now in the excited state, which was the 2. So what you have to do is think about this diagram and look at the minimal number of jumps you would have to take in order to get back to where you were. And that will sort of tell you the relative sort of probabilities of repopulating these states. But what it doesn't tell you is why you would have more 1s than 2s, because 1s and 2s are both L is equal to 0 singlet states. And there, what matters is that each time you apply these jump operators, they modify the wave function. So if you had a 1s state that was nice, let's say nice localized, and you did a bunch of these jumps, and then you come back, it's no longer has a strong overlap with the 1s, but it has a stronger overlap with the 2s. Because of the way these jump operators work. Now, I know this is not a very good physical explanation, but that's my explanation. It's tied up with how the wave function gets modified by the jump operators as it does these transitions. Because, for example, this first term multiplies the wave function by r. So if it was sitting down here localized in a nice 1s state, the leading order term spreads it out like that. And suddenly it doesn't look like a 1s anymore. It looks like a 2s. And if I keep applying them, it spreads them out even further. And eventually I would suppress its overlap with 2s and 3s. It would become a kind of unbound state eventually if I keep applying the jump operators. But if I have this sort of minimal set where it just does, like, say, 5 jumps and it hasn't gone completely to the unbound state, then I can get a kind of still well-localized state that has an overlap with the 2s. But the 1s is this super localized state compared to the 2s, and that overlap doesn't exist. That's my long explanation, but I don't have like a proof of this that I can just like pull out of my pocket and show to you.
Yeah. Okay. I think it does make sense on the localization and jumping. So yeah. Thank you.
No problem.
So since you have this slide on, let me throw in so you just took one of my questions. Let me throw it in.
Yeah.
No, very good. These suppressed terms that you added in, I don't remember that you showed us how important they are compared to the leading order contributions. How much?
Yeah, I didn't show everything I showed here was next to leading order. They turn out to be super important. Like okay. You find like order, it depends on the temperature. So at high temperature, they're not so important because these go like the binding energy over the temperature, but at temperature of around 200 MeV in the quark-gluon plasma, these can give you like 100% correction. And okay. That's what makes us worried that, maybe you want to get
the next one
the next leading order.
Yeah.
So, and that's it's on the to-do list. It's not in progress yet. But
well, yeah, I mean, it doesn't sound like an entirely trivial, simple thing to do, right? I mean,
well, it's the complication is that you can just do these diagrams, right, and get the self energies out and just systematically do an expansion in E over T. Then you get a result. But then you have to prove that you can cast the resulting evolution equations into this Lindblad form. Mm-hmm. That's the hard step, it turns out.
Okay. Very interesting. I mean, right, just given that your results look self-consistent and coherent, right, give you a positive feeling about this whole thing, but
right,
that's
if I wanted to show you it not, if you wanted to see it not working, I would try to do this with charmonium, and it doesn't work at all.
Okay, all right. Okay.
And that's because it might work for charmonium at Rick energies or maybe SPS, but well, also there I would be very worried because the temperature is low, and again this expansion, the scales get weird. But if I just try to apply it to charmonium at LHC, we get way too much suppression. And that's because there's actually many body recombination happening in the quark-gluon plasma in the charmonium sector. You can't treat it in this dilute limit. You imagine you just have a single bound state going and being perturbed. There's a bunch of open heavy flavor states that are just spontaneously reforming J size all the time. That's true. In heavy ion physics, we call that true regeneration. So we would have to expand this to density matrix to, now this full many body system. And yeah, so if you want to see it break, ask me to show you. I don't have one now, but it doesn't work. It doesn't work.
So one other thing that you could start thinking about is, okay, if you have a correction that turns out to be big. Now, if you have a qualitative understanding that this big correction brings in something qualitatively that has to be there, that isn't there at the leading order, right?
Yeah.
Then you might have another cause for optimism, right? If you know that, if you have an argument that at the next order, you don't expect something qualitatively new to happen.
Right.
Do you have any?
In this case, the one of the main reasons we wanted to go to next to leading order. So these terms that are sitting here are the difference between the singlet and octet. This the energy levels. And if you don't include that, actually, you'll never be able to thermalize the thing. Now, bottomonium thermalization timescale is probably 100 Fermi over C, so we don't really have to worry about it. But formally, it's at this order that you have to go before you can even ever possibly thermalize the state. So that's why at first our target was next to leading order. So that's the a key ingredient that you have to include to get to this order. And that won't get modified as you go to next to leading order. But I can't say at this point, quantitatively.
Absolutely. No, absolutely.
But things change dramatically.
At least this is a qualitative indication for something that's pushing in the right direction. Very interesting. Very interesting. Very good. All right. Do we have any more questions? What do you mean?
Yeah. So I wanted to ask with the jump operators. So there's that first term there that you mentioned, the R would increase the width of these, would increase the width when it acts on the, in terms of the wave modifier, the wave function. But in some of these, one of the T terms, right, in the interest of large quantum numbers, out, right, like how these transitions look. The pictures you showed were L equals to 0, L equal 1, and L equal 2.
Great.
If I was looking at saying large angular momentum quantum numbers, but would I necessarily see anything different in terms of that 1 over R factor? I would assume then that one would just acting on its own.
Yeah, actually, that's another qualitative difference that occurs when you include these next to leading order terms. So if you only look here when you're doing the jump always moves things to higher R, right? As you said. These things are the first next to leading order terms are just constants. But these ones that have 1 over R's and derivatives there, they introduce something qualitatively different. And in fact, instead of going to large R, the thing stays more localized because of these jump operators, for these parts of the jump operators. So yeah, these turn out to be super important for how you understand the evolution of the average R in the wave function when you turn on the jump operators. In practice, we don't truncate L, so we just let if it wants to go up to L20, we just allow it. But yeah, this term starts to become super important in that limit. Yes.
Very good.
And yeah, and then you're right. Just to that you should be worried that when L becomes too large, of course, the binding energy is going down. And yeah, the binding E over T. Yeah. No, it should work better for those states, but yeah, because the binding energy is going down. Sorry, I had to pause there to convince myself. Yeah, so the expansion, at least for those states, is okay, because the binding energy over temperature for the excited states is actually better than for the ground state. But yeah, in practice, we just apply these differential operators to the wave function and let anything that can happen. But yeah, qualitatively, instead of just going out in R, which would be what would happen at leading order, the combination of these next to leading order terms keeps the wave function more localized.
Okay, thank you.
No problem.
Any more questions? Yeah. Well, then let's thank Mike again. This was a heck of a journey through quite scary theory, I would say, right? I mean, didn't I say he doesn't shy away from hard projects?
Yeah.
But I think you gave us a very, very nice walk through that whole story. That was, I mean, if looking at the faces of my youngsters here, that was very nicely communicated. So thanks, particularly for that.
Okay, good. Yeah, I had to show some equations, but you know,
Good.
I need to focus on.
Yeah, but that was absolutely great. I had a lot of fun. So once again, great. We'll stop recording now. We can still chat a little.
Thank you very much.